Okay, so good morning, everyone. Today, Dr. Abhro Chando, I'll introduce him. So he will going to present the blue carbon. Actually, Dr. Chandra and myself, we start working since we are working since 2010, and he is an assistant professor in School of Oceanographic Studies in Jadavpur University, and where he is working a long stretch on the carbon, basically carbon dynamic in Sundarban estuary, and which is one of the largest estuaries and in the world. And Dr. Chandra is also very passionate in writing. So he has already published more than 100 peer-reviewed publications, with most of them with high impact factor, and he is very well in also in research. So today he will talk about the significance of blue carbon concerning the present climate scenario. And as we all know that the things are changing, the blue revolutions, so we are in the era of blue revolutions. So green revolutions already, we passed out, so we have to think about everything depend on the blue. So I welcome Dr. Chandra to take the floor, and after the session we will have a question answer. So I request all the participant, if you please unmute yourself, your mic, and you ask the questions after the his lecture. You can note down or send the message or your questions on the chat box. Okay, so the floor is open. Dr. Chandra, you can start.
Thank you so much. Thank you so much, Dr. Dotto. It is indeed a pleasure and quite a privilege for me that Dr. Dotto has actually invited me to share something that I have been researching on and learning myself for the last decade with you all. It's indeed an honor and privilege for me to be present here today and talk a little bit about the a very comparatively new concept that is blue carbon, which has emerged in the last decade or so. So, without understanding or rather anticipating that the audience, the learned audience, knows about blue carbon, I have framed this entire presentation into most essentially three different segments. In the first segment, I shall talk about the reason, or rather the driver, the need that at this point in time we are compelled to understand the efficacies of blue carbon and how they are functioning. Then I shall introduce the very concept of blue carbon, what it is actually, and why are we, the marine scientific community or the environmentalists, we are talking about it to this extent. And lastly, I shall exemplify with a suitable example, as Dr. Dotto has already mentioned. Dr. Dotto and we have been working on the world's largest mangrove forest of, in the Indian Sundarban. So I shall exemplify how blue carbon is so essential and what are the existential threats that these blue carbon ecosystems are facing, and how actually it can change the environment that we have already changed in the name of development, in the name of concretization, and so forth. So, moving on to the very first slide, as we all know, and I'm taking this liberty to just anticipate or comprehend that all the authors, or rather all the attendees of this seminar, they are very much well aware of the fact that we are living in an era where we have shown tremendous and callous disregard to our environment, not only by fossil fuel burning, but also by rampant conversion of green vegetation and several kinds of natural vegetative ecosystems. And owing to such phenomena or owing to such practices, now we have introduced substantial amount of greenhouse gases into our atmosphere. If we look into the levels, or rather the pre-industrial revolution levels, we have introduced carbon dioxide, methane, and nitrous oxide to such an extent that now the presence of those greenhouse gas and the alterations that it has led to the present day environment, they have now started hitting us back in the form of several hazards, disasters, storms, and whatnot. So even if we look at the current scenario, the present scenario, that is after the post-COVID scenario, during the COVID era, we observed a dip in all these kind of greenhouse gases because due to the lockdowns that we had to impose out of compulsion, these greenhouse gases and the emissions, the vehicular emission, the industrial emission, they stopped. And we could see that the environment, when it gets back to its previous best, that is in the absence of these emissions, how good they can be. However, as many of you know, that according to the Paris Agreement, each and every country, almost those who are part, or rather the party of the Paris Agreement, they have proactively come out and they proposed that we shall strive our best to limit the carbon dioxide, methane, and nitrous oxide, all these greenhouse gas emissions. And the target is to never ever at any cost to allow the world's global mean temperature to enhance beyond 1.5 degrees centigrade from what it was when the Paris Agreement was formed. However, unfortunately, as you can see in this slide, that 2021 emissions, that means when we started again going back to our original track after the COVID was over, we have started emitting at such an extent that it is now likely that within the next 9.5 years we can actually emit that much amount of carbonaceous greenhouse gases, which will in fact increase the global mean temperature to 1.5 degrees centigrade, and the net outcome will be catastrophic, as IPCC and all the people who are under this umbrella, who are under this joint fraternity, who believes that this shall cause an irreversible and irreparable damage to the world, shall come in to take place. So if we just look at the historical trends, and if we look at the principal three greenhouse gases that are fundamentally produced due to anthropogenic emission, you can see that there has been no declining order. A little bit of subtle change in the production has altered in the last, say, 1752. I have shown here 2017, but it is almost another 6 years has passed. So there is practically no, what should I say, no trend that is indicating that these raising columns that you can see over here in this graph, they will slowly decline. So there is a consistent and at the same time persistent increasing trend, as you can see here, that carbon dioxide is increasing at the rate of 1.61 ppm per year, methane at the rate of 15.6 ppb per year, and nitrous oxide is also increasing at the rate of 0.8 ppb per year. So now what we have done to our environment, owing to this kind of anthropogenic emissions and at the same time deforestation, mostly the green cover, we have been living in an environment before the Industrial Revolution where carbon dioxide concentration was around 278 ppm, and now it has become 408, and I guess by the time I'm talking, it is 410 or 12 in some places. Methane concentration has also increased leaps and bounds, and so has the nitrous oxide concentration. So you can see that previously there used to be a lot of green cover, and in the name of urbanization and in the name of development, again concretization, we have reduced the green cover, which used to be which always where the primary sink or the natural sink potential of the greenhouse gases, that is carbon dioxide, by means of photosynthesis, they take carbon dioxide, secure the carbon, and provide us oxygen. So those avenues by means of which we could have reduced the carbon dioxide load in the atmosphere, we have actually cut down those avenues for our betterment, for our development, which in no way is proven to be sustainable as of now. So just for those audience who do not essentially have the idea how a greenhouse gas is actually warming our atmosphere, this particular slide is only for them. It shows that if you look at this, the left hand side of the figure, the sun's solar radiation comes and strikes on the earth's surface, and the re-radiated heat gets transformed into the atmosphere, or rather into the space. Now, had this earth would not have had any troposphere where there were used to be greenhouse gases, then the earth could not have retained the minimal amount of heat that is required for not only human beings but multiple life forms to thrive. So greenhouse gases are very much essential. It is not like that we do not need any greenhouse gas in our atmosphere. No, it's wrong. We need greenhouse gases in our atmosphere, because unless there is greenhouse gases in the atmosphere, the lower troposphere will never heat up, and we shall end up like a barren planet like Moon, Saturn, Jupiter, or whatever you would like to imagine. But now, due to our wrongdoing, we have increased the greenhouse gases to such an extent that the lower troposphere is getting heated up. And the more it's getting heated up, all the phenomena that is being attached or that is being related with this lower troposphere, that is ocean atmosphere interaction, biogeochemical cycles and whatnot, they are being impacted, which is now hitting us back. So that's why global warming, ever since it was realized as a reality, we are always trying to find solutions, that how to prevent the global warming and how to combat the climate change by alleviating all those drivers that are actually leading to global warming. So before we understand or try to understand the role of carbon as a greenhouse gas and that leads to global warming, we must have an idea that what are the different pools where carbon is actually stored, or what are the different pools where carbon remains in this earth. So here you can see that terrestrial soil organic carbon, that is the carbon that is locked in the top strata, the top 1 meter of the global continental landmass, it is of almost this magnitude, 2500 to 3400 petagram. 1 petagram carbon means 10 to the power 12 kg. So all the soils are more or less, they behave in a heterotrophic manner and they actually emit carbon dioxide in this rate. However, the most important and intensive natural sink of carbon dioxide is the terrestrial GPP. GPP stands for gross primary production. That means the green vegetation, by means of photosynthesis, how much amount of carbon dioxide are they intaking in order to produce oxygen. So you can see that the terrestrial GPP is around 120 pgc per year. However, contrary to that, CO2 uptake by the ocean is very less. It is only 1.42 plus minus 0.53 pgc per year. And in atmosphere, almost 750 pgc carbon dioxide is there. So our main target, the entire world's target, is to reduce this load. The more carbon dioxide remains in the form of carbon dioxide and remains as biomass, as soil carbon, or in deep or dissolved in the ocean, it is better for the entire atmosphere. If the atmosphere has lesser burden of carbon dioxide, we are a happy people. Now, so carbon stored as fossil fuel in Earth's crust, it is almost about 4000 pgc. Now, every fossil fuel, it cannot be possible for human beings perhaps to extract every fossil fuel, oil, coal, and whatever the things they are hidden under the Earth's surface. But a substantial amount of these fossil fuels, we are, even though we have realized that burning of fossil fuel is not good for our environment, but eventually we are going to burn a substantial part of this figure, which means the load of atmospheric carbon dioxide shall increase in future. Now, the global scientific community have realized that while measuring that when we are emitting X amount of carbon dioxide, how much of that X amount of carbon dioxide remains in the atmosphere. Now, ever since the last decade, by the end of 20th century, the global scientific community realized that almost 50% of the carbon that we emit, they do not remain in the atmosphere. Now, that led to the global scientific community to question, then where does this carbon go? This carbon, if we are emitting in the form of CO2, methane, or whatever, then if I am not able to see the exact amount of my emitted carbon in the atmosphere, that means the additional, this quantity of carbon must be going somewhere and not in the atmosphere. So in order to find this missing link, actually, the global scientific community, they tried to, or rather they, from that point on, they strived to understand the changes in the biogeochemical dynamics that additional carbon dioxide load can impact, or rather can impart on the natural ecosystems. So studies actually accelerated both on the green ecosystems, that is the terrestrial vegetation part, and also on the oceanic ecosystems. And it has been found that the oceans are acting as a reservoir. That means the oceans are trapping a substantial part of the anthropogenically emitted greenhouse gas, because we are already delimiting, or rather we are not allowing the green vegetation to extend, or rather what it used to be 200 years back or 250 years back, because we have cut down the forests. So now at this point in time, the oceans are acting as a global carbon dioxide sink. So when it was realized that the oceans were acting as a global carbon dioxide sink, the scientific community felt it essential to color code carbon. Okay. So this blue carbon is nothing. Blue carbon is not a carbon that is colored blue. The blue carbon is just that carbon which is sequestered and locked for almost millennium by the coastal vegetated ecosystems. That means mangrove, seagrass, and salt marshes. Only these three ecosystems are known as the conventional blue carbon ecosystems. Because when we look at the carbon scenario, we find actually four types of carbon in present day world. Here you can see this is the black carbon, the carbon that is colored black. What are these black carbon? The black carbon are the remnant particles that remains as a component of combustion, but it was not fully converted to gaseous carbon dioxide. So this unburnt carbon that remains as soot particles, it remains suspended in the atmosphere. Sometimes they get deposited on the glacial ice caps or polar ice caps, and they enable actually to retain heat, and also facilitates the melting of polar ice caps and all those things. So these are black carbon. The carbon that is sequestered by the terrestrial vegetation, any vegetation, that can be tropical rainforest, temperate forest, boreal forest, any forest, that any forest or any vegetation which even might include the agricultural fields, that actually sequester carbon dioxide through photosynthesis, they are clubbed together as green carbon. Now there is another type of carbon where the carbon remains in the form of aerosols. Okay, aerosols at this point in time it's one of the most fundamental air pollutants, and it has its own significance. Sometimes aerosols are beneficial to us because it sometimes enables the sunlight not to come to earth and reflect back to space, but many times aerosols actually transmit the sunlight and increase rather absorbs the energy UV ray and deflect it back to earth, contributing to global warming. So my today's lecture is basically focused on this part. That is, here you can see a tree which is essentially signifying or emblematic of the mangrove plantation. And these are the sea grasses. Sometimes these can be over here salt marshes and sea grasses. Okay, so sometimes they are over here or sometimes they are submerged. But in the coastal periphery, where we call it the intertidal zone, blue carbon ecosystems only thrive over there. Now here we shall discuss that what is the significance of blue carbon. Why are we shouting so much about blue carbon? What is so special about blue carbon that is not there in green carbon? If these are the questions that we are looking for, then we must understand this, that salt marsh, mangrove, and seagrasses are such specialized ecosystems which can store disproportionately higher amount of carbon than any green carbon ecosystem and than the entire ocean. But if you look at the global map, these three ecosystems you cannot find these ecosystems in the heart of a continent or in the middle of an ocean. These ecosystems only thrive in the coastal boundary. That means the land sea transition zone, either in estuary or in the coastal boundary. So coastal boundary or and estuaries, they encompass altogether maybe 0.7% of the entire continental shelf, or sorry, the entire continental landmass. And within that entire continental landmass, mangrove, seagrasses, and salt marshes are also present in a very minute quantities. But despite that, these ecosystems have the capability of sequestering, that means snatching away the carbon dioxide from the atmosphere and keeping it locked for hundreds, thousands, maybe 1 million years. And that is why these ecosystems have gained so, I mean, ever since these potential of these ecosystems have been realized, they are now put under the lens, because they can actually enable us to sequester and lock more and more carbon and act as a true carbon sink to alleviate global warming. That is their only fundamental property. So now if you see at the global extent of the blue carbon ecosystems, you can see the green dots are the seagrasses. Seagrasses are available even in higher latitudes. Salt marshes are also available in the higher and lower latitudes. But mangroves, they are essentially tropical and subtropical in nature, so they are in this particular latitude. However, let me tell you that with increasing temperature, with global warming being a phenomena, the definition of temperate zone and tropical zone, it is becoming what should I say, that tropical zone is actually increasing towards the higher latitudes and lower latitudes, and sometimes mangroves are now being found even in the lower latitudes or sometimes in the higher latitudes as well. So this slide actually will tell you that what is the significance of blue carbon ecosystems compared to terrestrial ecosystems. So if you look at this particular slide, you can see that it shows ton CO2 equivalent per hectare. That means the carbon sequestration capability. So the seagrasses soil organic carbon can hold up to 500 ton equivalent of carbon per hectare, whereas all the tropical forests included, if I take the mean value, it is only 200. So compared to seagrass, salt marsh can accumulate 917 ton equivalent hectare CO2 equivalent per hectare. Estuarine mangroves 1600, oceanic mangroves 1779. Now I shall introduce, or rather try ask the attendees to very clearly look that our understanding about carbon sequestration is that the tree that is growing beside me, or the trees that we can see, their biomass actually holds all the carbon. Say for example, if you see at the tropical forest, the biomass, that is the living biomass, that is the stem, the branch, the leaves, they actually include 600 ton carbon equivalent of per hectare. But none of these blue carbon ecosystems have this much amount of biomass in their living biomass, or rather this much amount of carbon. Their strength is the soil. They can actually lock carbon in the soil or the sediment column more than any of the green vegetation. Any means any of the green vegetation, whether it is tropical, temperate, deciduous, any forest. The main potential of the blue carbon ecosystem is their sediment column. In the sediments, they can lock huge amounts of carbon. So if you look at the carbon sequestration potential over here, you can see that for temperate, tropical, and boreal forests, this compared to this forest, salt marshes, mangroves, and seagrasses, they store up to the carbon sequestration potential, that is gram carbon per meter square per year. That is almost 3 times higher than any of the green ecosystems. So you have to understand one thing, that these blue carbon ecosystems or marine ecosystems have an advantage over the green carbon ecosystems. And what is that? Green carbon ecosystems can only take directly atmospheric CO2 through the leaves. If we go back to our elementary days, we know that the leaves have stomata, and through the stomata, the carbon dioxide gets in, and the green plants that we see around us, they can carry out photosynthesis. But the submerged vegetation, they have over time acclimatized themselves in such a way that when atmospheric CO2 becomes dissolved CO2 in water, it produces carbonic acid, and this carbonic acid, as we know, is an unstable compound that it dissociates as bicarbonate ion and H plus ion. Okay, so this bicarbonate ion, they can directly take up. These plants, seagrasses or salt marshes, when they are submerged, they can actually directly take up bicarbonate ions from water, not CO2 from air. So that is an added advantage of these particular plants, that they have developed, or what should I say, they have changed themselves, modified themselves, and altered themselves in such a way that they have become a very crucial pathway, a very efficient pathway to actually absorb carbon, not only from water as well as from atmosphere, because the mangroves, they always remain, mostly they remain exposed to the atmosphere. So the mangrove trees, if anyone has seen a mangrove tree, or since many of you are from Oman or from many different parts of the country in the coastal periphery, when you see a mangrove tree, you can actually see not a very basic difference between a green plant and a mangrove plant. So they can take atmospheric CO2 as well as they can take oceanic CO2. Now here you have to know one more thing, that coral reefs are not conventional blue carbon ecosystem, though the fact they are a very crucial ecosystem, a very crucial marine ecosystem. They provide innumerable number of ecosystem services, but coral reefs are not essentially blue carbon ecosystem. Why is it so? Because whenever a coral reef formation is taking place, the calcium ion of these calcareous organisms, when they form calcium bicarbonate or calcium carbonate, they actually emit one carbon dioxide molecule. That means they cannot act as net sink for carbon dioxide. Their building process is as such that they have to emit one carbon dioxide molecule, which means corals are net zero functioning marine ecosystems. They are not contributing to sinking carbon dioxide. They are actually not positively contributing or not negatively contributing. They are neutral. And that is why coral reefs, despite being one of the most essential marine ecosystem, is not considered within the conventional arena or realm of the blue carbon ecosystems. Now, if you look at the fate of blue carbon in the marine ecosystems, and at the same time, why blue carbon ecosystems are so crucial. In order to understand the cruciality or the efficacy of the blue carbon ecosystems, you have to first take into account that where this kind of ecosystems actually thrive. I have mentioned it before that they thrive it in the land ocean boundary. Now the land, the entire continental land mass, it is always acting as a source of carbon. All the kinds of carbon that escapes the terrestrial vegetation, either through rainfall, runoff, dissolution, weathering, anthropogenic carbon, that is unburnt carbon, hydrocarbons that actually sometimes end up in the rivers. Every one of those carbon sources, they come and meet the ocean. So there they are guarding the entire ocean land transition zone. And in the realm of blue carbon, there are two terms that we use. One is autochthonous carbon, that is the carbon that is directly sequestered by them. And then there is allochthonous carbon, that means the carbon that is not sequestered by them, but the carbon that is coming into these ecosystems, and they are acting as a filter to trap them and to send them down, that is towards the this new the pedosphere or the rhizosphere or the soil, as you would like to imagine. So here you can see that these ecosystems previously used to be in this level, and with rapid sedimentation and all, they usually rise up. So new carbon which is sequestered in the upper layers, they shall become old carbon in the next 100,000 years. And once the carbon reaches these deeper layers, they remain locked in these layers. And these carbon, often they form pit formation takes place over here. So these carbon altogether acts as a reservoir by means of which you are actually snatching away carbon dioxide from the atmosphere and enhancing it in rather locking them away from the atmosphere in the form of organic carbon. So we actually want this fate of blue carbon to remain intact. However, I shall proceed to the next slides. You will see that it is our own doing that is actually compromising this character of sequestering carbon within the blue carbon sediment column. So this is just an overview of the present or the global extent of in terms of million hectares. So you can see mangroves are from 13.8 to 15.2 million hectares mangroves are present right now. Seagrasses are estimated to have this value. salt marshes. There are still credible amount of doubt that how much salt marsh does global this continental shelf margins can have, but more or less these magnitudes have been mapped. But what is our point of concern? The point of concern is that due to anthropogenic activities, we are converting. That means we are destroying these ecosystems at the rate of 0.7 to 3 million hectare per year, 0.4 to 2.6 million hectare percentage per year, 1 to 2% per year. So if this continues, if this goes on, then maybe in the next century or by the end of 2200, the world might be devoid of all these blue carbon ecosystems, because they have this carbon emission due to degradation range of this particular magnitude. So in order to understand this, you have to understand also the very crucial aspect of blue carbon. That is why I have titled this blue carbon thing as a double-edged sword. Blue carbon ecosystems has the potential of sequestering disproportionately high amount of carbon. That's true. That is why we are trying to take advantage of these ecosystems, and we should conserve this ecosystem, and we should allow these ecosystems to enhance, so that more and more carbon dioxide is trapped by these ecosystems, and it can help us alleviate the load of carbon dioxide. But at the same time, we have to keep in mind that if we do not conserve blue carbon ecosystems, if we become negligent and allow these ecosystems to be destroyed or diminished, then a blue carbon ecosystem acts as a huge source of carbon dioxide as well. Which means, if I put it in simpler word, if I destroy 1 unit area of a tropical forest, I can emit, say, X molecules of carbon dioxide. If I destroy 1 unit area of a mangrove forest, I might emit 10x times of carbon dioxide. Why? Because the load or the carbon that is accumulated in a blue carbon ecosystem is very high. If I allow the carbon to get remineralized, if I allow the microbial activities, and if I just destroy the mangrove, uproot the seagrasses, and destroy the natural functioning of this ecosystem, all the carbon that these ecosystems have been sequestering for the last million years, they shall emit back to the atmosphere, and blue carbon ecosystems can actually act as the very high source, very high source of carbon dioxide towards the atmosphere. Hence, we have to keep in mind two things. We have to conserve blue carbon ecosystem. Once they are conserved, then we have to think that how can we increase their extent so as to gain in our favor, so as to use the blue carbon ecosystems in our favor. So if you look at the different types of carbon fluxes, I'm sure many of you are not aware with the word flux. Flux means that exchange of matter or energy within, rather between two systems per unit area, per unit time. So over here in blue carbon ecosystems have several different types of compartment. The atmosphere biosphere carbon flux is that the green vegetated part, how much means the green leaves or the green parts of the blue carbon ecosystem, how much carbon dioxide they can actually fix through photosynthesis. Then litter fall, that means how much of the dead leaves, dead roots, dead decaying matters are actually entering into the soil. So these two factors essentially incorporate or rather enhance the sink strength of blue carbon ecosystems. However, if we look around the water beside the blue carbon ecosystem, they mostly behave as a heterogeneous ecosystem. That means they emit carbon dioxide towards the air. The soils also, the topsoil, that is the soil that is in contact with either water or atmosphere, they also most likely act as the source of carbon dioxide towards the atmosphere. However, in totality, these two green arrows always supersedes these two red arrows. Hence, in totality, the blue carbon ecosystem should act as a net sink for carbon dioxide. Now, moving on next, I shall very quickly show you that what is exactly happening with a very crucial blue carbon ecosystem of the entire world. The map that you are seeing over here, it is the map of the Indian Sundarban Biosphere Reserve. Now, Sundarban is the world's largest mangrove forest. It is shared by India and Bangladesh. 40% of Sundarban remains in India at the present date, and almost 60% is in Bangladesh. Myself, Dr. Datta, we being Indian, we have had the honor of working in the Indian Sundarban to a great extent. And today I will talk about I shall use the example of Sundarban to show you that how, at what rate blue carbon ecosystems are being converted and what kind of damage we are actually incurring by ourselves. So if you look at this map, at this particular section, despite being a part of the mangrove ecosystem, this light gray section actually hosts around 4.5 million people. That means it is thickly populated. And the remnant of this section, this is the mangrove forest. The light gray portion is the buffer area where certain activities the Indian government or the West Bengal State Forest Government has allowed for the fishermen and the various other communities for to carry out livelihood activities. And the rest of the part is the core area. That means any kind of human intervention is not allowed. So if you look at how this ecosystem is behaving, we have measured. I have had the honor of conducting some experiments on the Sundarban, and I clearly found out that during the daytime, the Sundarban mangroves are acting as a very high sink of carbon dioxide. During the night time, they are respiring. Yes, it's true. Of course, any tree respires back CO2 during the night. But if we look at the sinking strength, the sink strength is much higher. That is, if we look at the flux of carbon dioxide, that is FCO2 in milligram per meter square per second, the values are going as high as 2, 2.5 during day, and the positive values are 0.5 to 0.6 during night, which means in totality, it is acting as a net sink for CO2. So if I look at the soils, like almost all blue carbon ecosystem soils, they are acting as a source for both carbon dioxide and methane. Okay. So, and we have found that as the temperature will increase, the soil microbial activity will increase and the soil CO2 efflux shall also increase. Okay. So this has been the primary observation from Sundarban. What about the water? I'm not going into the intricate details of the aquatic chemistry, but we have also found that the estuaries, the rivers, the nearshore coastal waters, they are all acting as CO2 efflux. That means they are acting as source of CO2 towards the atmosphere. Now, you might think that if so many things are acting as a source of CO2, then what is what is the need for having blue carbon ecosystems? But if you actually look at these magnitudes, then you will understand that in totality, despite the soils acting as a source, despite the water acting as a source, in totality, the ecosystem is acting as a sink. You look at the magnitude of this carbon dioxide flux, that is mangrove soil to air CO2 flux, it varies from 1.4 to 33.2 gram CO2 per meter square per day. If you look at the water to air CO2 flux, mangrove adjacent water to air, it is 0.03 to 10.2. However, if you look at the magnitude of carbon dioxide total intake by mangrove vegetation from air, it is 284 to 2972, which is an order of magnitude higher than these two values. That means in totality, this vegetation is acting as a CO2 sink. That means net CO2 is being sinked into this particular ecosystems. So if I look at the carbon that is locked within the mangroves, then you can see that the entire above ground biomass is of around 16 TGC. That means teragram of carbon. 1 teragram means 10 to the power 12 gram. Okay. So if we look at the entire live below ground biomass, it is almost 5 teragram. And if we look at the soil carbon pool, it is almost 5.5 teragram. Now, I have just in the earlier slide said that it is the strength of the mangrove ecosystem, seagrass ecosystem, and salt marsh ecosystem that the main portion of carbon that remains in their soil. But here you can then counter ask me, then why it is so low? 5.5 teragram carbon, and the above ground biomass is 16 teragram carbon. This should not be so low. Then why did you say that the main strength of blue carbon ecosystems are that the sediment carbon profile will have more carbon than the live above ground biomass, unlike the green vegetation? This is actually acting as a green vegetation, not acting as a blue carbon system. So now, in order to understand that, I shall take you to what are the threats of carbon sequestration potential to the Indian Sundarban. You can see I have enumerated 6 crucial points. First, anthropogenic encroachment. Second, reduced freshwater supply. Salt stress management or salt stress on mangroves. Expected change in species composition. Erosion of mangroves. And finally, cyclonic disasters. So these 6 are the fundamental things that is actually inhibiting the blue carbon ecosystem to act in a way that it should have acted in a world without these anthropogenic threats. First, human encroachment. You look at this map of Indian Sundarban and you can see that there are 6 maps. The first one is 1776. It was during the time of colonization when the Sundarban deforestation actually started. Then in 1873, you see a substantial amount of vegetation, they disappeared. Now these areas at this point in time in India, they are completely urbanized. So at this urbanization happened at the cost of destruction of mangrove, which is nothing but a blue carbon ecosystem. Then 1968, almost two-thirds of the Sundarban is gone. 1989, within the Sundarban, these green patches that you can see now, they are thinning as well. That means the vegetation cover, the canopy cover of the Sundarban is now getting compromised. And lastly, in 2014, the study from which I took it, they conducted it, their last measurement in 2014, only this much of Sundarban remains. Now, more or less the same thing is happening all around the global mangrove, global seagrass, and global salt marshes. Due to our encroachment towards the coastline, these ecosystems are suffering. So, population in 1951, that is in India, just after independence, in the Indian Sundarban Biosphere Reserve was 1.15 million. And as per the last census, it has increased to 4.44 million. So this push by the population towards the sea is actually squeezing these blue carbon ecosystems as a sandwich between population at one end, population derived urbanization at one end, and the ocean in the other end, which is continuously rising, because regional sea level rise is more or less a phenomena in every coastline of the world. Now, if we squeeze these ecosystems from both ends, then how will they perform, and how will they help us in acting as more and more carbon dioxide sink? That is number one. The number two part, the reason why you found that the below ground Sundarban compartments, that is the soils of Sundarban, despite being the largest mangrove forest in the world, has so much less carbon. Why is it so? Because, as I have mentioned, the criticality or the efficiency of a blue carbon ecosystem is not that they can sequester very high amount of carbon. The efficiency of blue carbon ecosystem lies in the fact that they can not only sequester carbon, but they can also filter carbon, the carbon that comes from upstream. So if you look at this map, mine and Dr. Dotto's supervisor, I think he has also given a lecture to you all, that is Professor Sugato Hajra. Professor Sugato Hajra and his scholars, they carried out a study, and they found that all the upper ties or the estuaries that actually flow into this Sundarban ecosystem, the main rivers that usually used to carry the fresh water to this particular ecosystem, that is the Sundarban, they have been detached. They have been disconnected, and as a result of what, fresh water is not coming into this part. Fresh water is a source of carbon for this part, and this carbon, which is not sequestered over here but comes through fresh water, they are actually filtered and put to the sediments. In the absence of fresh water, the salinity is increasing and the carbon load that should have increased is decreasing. So now Sundarban's soil, when it erodes, it's give away far more carbon than actually storing. So every ecosystem, every blue carbon ecosystem actually should function well if the proper connections between that blue carbon ecosystem and the inner terrestrial counterparts are maintained. If you stop those connections by building dams, by encroaching rivers, by allowing indiscriminate urbanization, even if you carry out this activity higher upstream, all those activities are going to pay for all those activities. These blue carbon ecosystems in the land ocean boundary, they have to pay a very high price, and this is the price Indian Sundarban is paying for indiscriminate urbanization, population growth and development, which is actually cutting off all these arteries, all these veins that used to provide Sundarban with carbon. Now, I have already mentioned that the water, the fresh water that used to come over here, it's not coming. And as a result, the immediate next thing is that Indian Sundarban is experiencing salinization. Mangrove, seagrass, salt marsh, all these ecosystems, they are salinity, rather they can endure salinity, and that's why they are marine ecosystems. But you cannot group them all together. You cannot say that any and every mangrove species can withstand any and every salinity. There are certain species which prefer to grow in less saline region. There are certain species which prefer to grow in high saline region. Now, those species which used to grow in less saline region, in the presence of fresh water, they are now getting diminished. Why? Because the salinity is increasing to such an extent, they are not able to withstand such an amount of salinity, and hence they are becoming regionally extinct. So here you can see that what happens if excessive saline water actually comes in contact with mangrove trees, because mangroves have some mechanism by means of which they tackle salt. Some of the mangroves are salt excluders. That means they can exclude the salt and only take the fresh water. Some of them are salt secretors. Here you can see they can secrete salt as separate salt particles. And some of them are salt accumulators. That is, they can see they can accumulate a part of salt, some part of salt in their salt glands. So there are these kind of glands in this mangrove forest where they can actually retain some amount of salt. But when you actually expose those mangroves to certain salinity conditions, when all their natural mechanisms fail, eventually you will see the top dying syndrome. That means the canopy cover will slowly start to die off. And if this canopy cover starts to die off, the natural photosynthetic potential of accumulation of carbon dioxide, you are robbing the mangroves from that. Hence, they cannot perform as an efficient blue carbon ecosystems. They cannot perform as an efficient carbon sink. And that is happening because of us. We are changing the salinity dynamics. We are changing the dynamics of freshwater and seawater admixing. And because of that, the mangroves are paying in this way. Now, what other things will happen if the salinity changes? If the salinity changes, there has to be a rampant shift in species composition. As I have just already mentioned, only those species will survive which are salinity tolerant. And those species which are not so salinity tolerant, they will become extinct. So I carried out a study myself in 2016 just in order to see that if the species diversity changes, then what impact will it have on the blue carbon stock? Unfortunately, we found that the low saline species used to have the highest number of, or rather the highest magnitude of carbon in their trees or in their soils. So, for example, Heritiera fomes, Nipa fruticans, Seriops decandra, these are certain species which in India they are, I mean, freshwater loving species. But this freshwater loving species had the potential of sequestering higher quantities of carbon. Now, these freshwater loving species are almost virtually absent in the natural landscape of Sundarban. They have been replaced by the high saline species. The high saline species will increase. They are projected to increase. Here you can see the year 2015, 35, 65, 2115. So if they increase, and they decrease and the mid-saline species remain almost the same, inevitably it is actually loss of ecosystem service. Why? Because you look at the y-axis of the low saline species, it can go up to 45 teragram of carbon. However, if you look at the high saline species, it can grow even after 100 years, it can go only up to 20 teragram of carbon. That means even if they are replaced by a high saline species, the carbon content will inevitably be compromised. The total carbon content will inevitably be compromised, and which means that this amount of carbon, 45 minus 20, this amount of carbon will be actually in some way or the other emitted back to the atmosphere as carbon dioxide. Now, lastly, or rather the penultimate clause is the erosion of mangroves. Due to both regional sea level rise and at the same time absence of water, we are also fundamentally hampering the entire landscape of this ecosystem. Why? Because this ecosystem is not just a mangrove ecosystem, it's a deltaic ecosystem. And the deltaic ecosystem cannot thrive if the ecosystem do not receive sediment. So by hampering the freshwater cycle, we are actually not allowing, or rather not giving fresh water, number one. We are not giving carbon that comes with the freshwater, number two. And lastly, and very crucially, we are not providing adequate amount of sediment to this blue carbon ecosystem, which can form the basis or which can form the substratum where they can store carbon. So we are actually taking away sediments. Now seawater is gushing in and going out. So sediment profile is actually getting weak. The top sediment is getting removed, and that is why Sundarban is facing net erosion. If my blue carbon ecosystems soils are the primary reservoirs, I have to add soil. I cannot take soil from from those kinds of ecosystems. However, unfortunately, anthropogenic activities are now taking away soils. So once the soil goes, you can see I have given two pictures. Once the soil, they are being eroded, you are actually exposing these ecosystems because they are the fundamental pillars of this ecosystem as a whole. Now, once the soil is gone, the carbon is gone, and at the same time, I am making them weak so that a tree which was standing at some point shall no more or shall cease to exist at that point. So how can I expect that they will trap carbon dioxide from me? How can I expect that freshwater carbon will be stored over here even if I provide freshwater carbon? So sediment dynamics is something that we have changed in almost all the coastal sectors of this entire world because of our doing, because of our dams and barrages and all those things, and the blue carbon ecosystems are paying for them. And lastly, it is a natural disaster. I mean, almost all the coastal ecosystems sometimes or I mean, maybe once in a year or maybe once in a 5 year, they have to face some natural disasters. It is not like that we can do much about them. But yes, it is also true that it is because of our doing. The frequency, there is a debate about the frequency of natural disaster. But one thing is for sure, the intensity of natural disaster has increased. Say, for example, what you have seen in Dubai in the last couple of days, what we in Indian Sundarban have seen in the year 2020, that Amphan passed away, the severe tropical cyclones, they are forming in the Bay of Bengal and straight away hitting either India or Bangladesh, and rampant destruction of mangroves are taking place. But the thing is that mangroves do have the natural recovery potential. But if these phenomena starts happening again and again, owing to climate change, for which again we are responsible, the mangroves will not get enough time to recuperate. Because all the factors that I have discussed, you cannot show me one factor that is actually acting in favor of the mangroves. All these factors are actually acting against the blue carbon ecosystems, against the foundation of blue carbon ecosystems. So what is the need of the hour? We need academic intervention, we need interdisciplinary research, and the output of such academic intervention and research must be actually exhibited, or must have a channel or avenue with the policymakers and the conservationists. They should consult the academicians and they should sit together, and they must ensure that the net outcome from the policymakers, conservationists, and academia, it should be reflected in policies taken by government levels for not only the restoration that I am actually trying to highlight, because instead of enhancing restoration at this point in time is very crucial. There are several degraded blue carbon ecosystems. Our first aim should be to restore them and make them a proper functioning blue carbon ecosystem. And once we can actually restore, then we can think that how we can actually extend their area, enhance their area, and use them as an efficient tool to combat climate change by uh, allowing them to sequester more and more CO2. So it's a book that I have written on the blue carbon dynamics of the Indian Ocean. If the authors, the attendees, if they are interested in reading the book, here's the link is given. I can share it with Dr. Datta. The soft copy of the book is as well with me. If you want to have more in-depth knowledge about blue carbon ecosystems, you are always welcome to read this book. And I shall end with this key message to every listeners and every attendees, that we have already lost a substantial part of Amazon rainforest just a few years back due to exclusively due to our wrongdoing, and we are sitting in an era where we cannot afford to lose any more forest, whether it is blue or green or anything. Thank you all. Thanks to Dr. Dotto and for enabling me or allowing me to give a speech today. Thank you all. Thanks for your patience.
Okay, thank you, Dr. Chandra, for a wonderful speech. And yeah, it's a very interesting that if yeah, even I think all the participants who are attended the concept of blue economy, it's now blue carbon, it's now clear, and it's very interesting. And a few things is also very crucial to know. The new thing that even yes, the corals are not contributing or not considered as a blue carbon. So that's a few things is very interesting. I am opening the floor to the participant to the questions. So if you have any questions, so you turn on your mic and ask Dr. Chando. And yes, he is very expert in this field. He's working almost, I think, 14 or 15 years almost in this a region and on specifically the carbon dynamics of Sundarban estuaries. Okay, so the floor is open to the participant. If you have any questions, so please ask Dr. Chandra. Any questions?
Hello, good afternoon, Dr. Chandra. Am I audible to you?
Yeah, I'm heard. Good afternoon. Yeah.
Good afternoon, yes, your lecture is wonderful, and for the first time, we are learning in depth and seeing about the things via GIS map and all that you show that Sundarban are thinking and all. So, sir, my question is like very basic. So, as in the last you have mentioned that the academic intervention and research needs to be the part of the horse, and that also like with the policymakers. But sir, the thing is that here, like policymakers, like in everywhere there is a greed. So, in despite of taking the results from the researchers and the things, they just take up and they wind up, and when it come to the implementation and all, so the implementation bodies and are very weak. So what are the things that should be like done by the people, because like people are the one who meant to do the things. Like we cannot depend on government, NGO or any other bodies for enforcement and all, because as you have told that the sediments that are coming from fresh water things and all from the high altitude and all, and it's bring carbon. Yeah, that's true actually. Yeah, and but the thing is that the sand mining that is happening in and around the freshwater bodies, the rivers that are flowing from the hilly areas and all, they are doing mechanized rampant sand mining. Right now, I am here in Meghalaya, and what I
Right.
see here in the rivers, what they are doing, as you have told that they are building dams and things and all, and they are taking off all those things. And the thing is that
Right.
now the wisdom is dying. he places those where throughout the year streams are flowing, that streams are drying up. They're drying up actually
Right.
because they have changed the river course, and the water that is like flowing at the rate of means naturally, but due to our anthropogenic things, it increased. And now in its increase, it take up all the things, all the things. So, sir, what is the
Right.
thing that a person or an individual or a community should do? That like I would like to have your like suggestion on it. Yeah,
Well, thank you. Thank you very much for this question. See, this is a question that has been intriguing all of us. Okay. And it's not
yeah,
like that uh, 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 just the marine scientific community, but almost every scientific community. When a scientist performs research, conducts experiment, he expects to bring out certain results, which unless implemented, it's as worthwhile as not doing research, as worthless as equivalent to not doing that research in the first place. But you see, this just because the government is not doing this, the government is not doing that, we can always blame the government. That's the most easy thing to do. But at the same time, I think, since we are not the government people, I mean, you and I are not going to join politics and become a leader or become a politician just in order to save the natural ecosystem. You cannot do that. But we must actually, I mean, what should I say? We must strive to actually build awareness, among the locals. Among the locals, and not only among the locals, but also we must always try to knock the doors of the government through, of course, influential channels, so that they can actually tell the story that if you do this today, you might be a short term profiteer, but in the long term you will be a loser. Okay. And with the intent and with the expectation that someday there might be someone who will actually understand and try to implement. Say, for example, from the perspective of blue carbon, let me say, australian government australian government have actually incorporated the concept of blue carbon in their constitution, because Australia has
oh,
ocean everywhere. Okay. And they have like mangroves, seagrasses, and coral. They are trying to restore their mangroves, they are trying to restore their ecosystems. But then again, they do not have the population pressure that we have. So, like in India, also there are regulations. There are regulations like ICZM, integrated coastal zone management, is there.
yeah,
Dr. Doc himself is an expert of this ICZM, who is actually abiding by the ICZM. Everyone is violating ICZM and building tourist resorts in the land ocean transition
yes,
zone, knowing the fact that the resort even will not be there in the next 30 years. It will go to the sea. But
yes,
everyone is actually looking at short term profit. But I guess this is not a call, or rather, this is not a reason for which we scientists should become, we should get demoralized. Because, let me tell you something. We are in 2024 or 25, so we are living in an era where everything is increasing. Okay. Population is increasing, economy is increasing. If you look at every country, it's increasing. But by the end of this century, global population will start to decline. Okay. I'm
that's true.
not listening very much about from any country or from UN, that how we shall actually tackle that kind of problem where our existential identity will be under threat as human beings. We are busy quarreling amongst each other. Okay. But
Yes, yes, that's true.
we must not lose our intent. Number one, we must not feel demoralized, because if we feel demoralized, then the last hope for this natural environment is gone. So very soon we shall leap into a world where population will not be the factor for which you will be compelled to destroy environment. The next phase will be simply the government's intent or not. We have to keep this fight on, that see, we are doing this research and we have some finding. You please try to read and understand that this is going to be a long term damage in the year 2100. Say, for example, there are some certain studies which show that China's population in 2100 will be 40 crore. India's population will be 80 crore, which means immense population reduction will take place. So, if population reduction takes place, these natural ecosystems, you don't have to spend a single rupee in order to restore a marine ecosystem. They will restore themselves. It is that we are actually encroaching their space.
Yes,
Okay,
that's
so
true. That's
our
true actually.
work is to do good work, and our work is to educate the people. We can't turn into politician just because our work is not being taken into granted. But that is no call, that is not an excuse that we shall stop doing our work. So,
Yes,
Suraj, I guess, right? If I'm saying Suraj Pratap Singh, yes. So
yes,
you and
sir.
I are both in the
Yes, sir.
on the same page, and we have to keep this fight on
Yeah.
for our sake, for our next generation's sake. So practically, if the I could not answer your question because I do not have any idea that how to answer your question. That how can I influence a politician to understand that what is the significance of blue carbon? Because about blue carbon is a luxury in the panorama of Indian politics where so many things are happening. But
Yes.
we should be actually striving hard to do what we are doing best, and the most essentially we should keep this chain or the flow of knowledge on, so that our next generation at least knows about it, that someone in our earlier generation talked about it,
Yes.
then you didn't listen, now at least you listen. Okay, so that
Yeah.
should be the spirit,
That's
I
true,
guess,
sir.
instead of an accurate answer. Thank you for your
Yeah.
question,
That's.
Suraj.
Thank you. Thank you so much, doc. Thank you so much, Dr. Chandra. Thank you so much for your valuable
Most,
Yes.
feedback
most
on
welcome.
it, and like I'm very happy to be a part of it. Thank you so much, Sajnan sir, also Pratap sir, for like
Thank
always
you.
doing this type of webinars and all. Thank you so much.
Thank you. Any other questions? I saw two hand rise. Anyone have questions? Yes.
There is one question in the chat.
Uh,
Yes, yes.
which one? That's my question. Is that in previous slide it was corals. Corals do not serve as a substance. Why the corals is not? Yeah. And however, it's commonly understood the corals are indeed a part of the natural cycle, carbon cycle. And could you please elaborate whether the corals adversely affect on the ocean environment about the carbon dioxide?
Yes. Actually, see, uh, the concept of blue carbon, it came in the year 2009. Okay, so which is just 15 years back. Now, what happened? There are some school of thoughts, or rather schools of thoughts, who thinks that this blue carbon ecosystem arena can be expanded. Not only corals, people are now arguing about kelp, seagrass, macroalgae, the phytoplankton, all these things to incorporate into the system of blue carbon ecosystem. Now the thing is that when we are talking about any ecosystem which has the potential to sequester carbon for a long time, okay, that can only act as blue carbon ecosystems. At least those who believe in the conventional concept of blue carbon ecosystem, they believe that carbon can only be locked away from the atmosphere in the organic form. In the organic form, if I can exclude carbon, and if I can exclude it to such sediment depths where microbial activity cannot reach, then it is possible for me to sequester carbon. But corals are completely inorganic carbon. It is calcium carbonate and calcium bicarbonate. So if the pH of the ocean increases, which is actually happening, ocean acidification is taking place everywhere in the world, the corals will dissolve. The corals will simply dissolve and there will be no corals. So the conventional blue carbon thinkers, they are arguing that coral do not have the mechanism to store carbon beneath coral. Coral themselves are carbon, but inorganic carbon. Inorganic carbon which is highly susceptible to dissolution or dissociation, and hence all the carbon, if the corals do not, they themselves do not remain, then where the carbon will go? The carbon will straight away get dissolved in the water and it will be emitted back to the atmosphere as CO2. Now blue carbon ecosystems like mangrove, seagrass, coral, they also have inorganic carbon, but inorganic carbon in the soil remains at a very minute quantities. Most of the amount of carbon that remains in the blue carbon soils or sediment profile, they remain either as organic carbon, This organic carbon has various types of this organic macromolecules are there. Lignin, tannin, these are the complex macromolecules which are not easily acted upon by the mangroves. And then there are some other compounds which are easily acted upon by the mangroves, and they eventually get dissociated into CO2. But if you have a steady organic carbon burial mechanism, then by default, slowly the organic carbon, a part of the organic carbon will go into the depths of the mangrove, seagrass and coral ecosystem, salt marsh ecosystem. They have that sediment profile. Corals do not have that sediment profile. Corals are just a benthic organisms which are growing on a benthic substrate. They are a fascinating ecosystem. There is no questions asked about that. They provide fishery, they provide n number of ecosystem services. There are studies which show that corals are acting as a guard to facilitate the growth of seagrass and mangroves, because corals always grow towards the seaward end. Seagrass, salt marsh, mangrove, they grow towards the landward end. Corals are acting as a barrier of physical disturbance. If a strong wave is coming from the ocean to destroy the seagrass, salt marsh and mangrove, corals are acting as a barrier. So corals are in many ways useful in n number of ways, uncountable ways, also to the blue carbon ecosystem. But the corals themselves are not blue carbon ecosystems. That is the idea. That is the very subtle difference that one should know.
Thank you, sir. Thank you so much.
Good. There is a one questions about carbon market.
Ah. So carbon market. Okay. So yes, if you personally first ask me whether I am a proponent of carbon market, at some point in time, I used to think that this thing can solve, many crucial factors. But now with each passing day, I feel that carbon market can actually not act as a very efficient solution. Even if I go a decade earlier, the way they used to think that, okay, this can be the answer to all the problems. What is carbon market? First, you have to understand that. Say, for example, you live in a country where there is no blue carbon ecosystem. You are a landlocked country. Okay. And you are emitting some fossil fuels, burning some fossil fuels, doing some destruction of your own vegetation. But you are somebody who is from a rich country. So you are actually ready to pay someone in a poor country who has blue carbon ecosystems, that you please conserve your ecosystem. I will pay you something, and by paying you, I am actually legalizing or earning a license that I can continue emitting in my own country. Now, it sounds good that somebody is ready to pay in order to conserve any ecosystem. Carbon market is not like that it's only applicable for blue carbon ecosystems. It was actually initially thought for green ecosystems. Okay, that conserve forest. Who will conserve forest? The local people who live around the forest, they will conserve forest. Who will conserve the blue carbon ecosystem? The local people who live around the blue carbon ecosystem. They shall compromise their profession and safeguard the blue carbon ecosystem. Someone will pay for them. Someone will say that you do not do agriculture. You simply protect your forest, protect your mangrove. I will pay you. That is the principal idea. The idea is very good, undoubtedly. But the problem that the world has faced in the last decade, or maybe the last 2 decades, that there is not a proper implementing mechanism. There is no proper avenue suggested by any authority that how exactly this carbon market can be introduced. Okay, clean development mechanism can be introduced. So due to this lack of proper avenue, what's happening, there are some intermediators who are actually taking the money. They are promising that I will give that particular community. That community safeguards the forest or any particular X amount of area where carbon is locked, and then they are not getting paid. So this lack of change, this lack of proper avenue is actually making things very difficult, because once that particular country or that particular payer who is ready to pay for carbon protection, that country needs to know that how much carbon you are protecting. Tell me at first. So when this question comes into place, then you have to have a proper protocol to estimate that this much amount of carbon is there in this unit hectare area, and I shall protect that. Now, if I am talking about a land area, which can be of mangrove, which can be of a tropical rainforest, if I am the beneficiary, then I shall always say, okay, I have 2000 carbon in my land area. But then if they come and see that maybe I have only 100 carbon, I will always tell that I have so much amount of carbon. So who will measure how much amount of carbon is there in the first place? Who will actually monitor that how much carbon is actually being stored and not allowed to destroyed? So unless you have all these proper implementing mechanisms crystal clear, that transparency will be maintained both on the beneficiary's side and on the side who is ready to or who is willing to pay, this entire mechanism cannot exist in reality. That is the problem with carbon market. The idea, the concept is very good, but in case of implementation, it is failing. It has failed everywhere, I guess. Even if those who claim that no, it has worked in our case, there should be something shady that, I mean, they are not either not able to encounter or not willing to state, to be honest.
Good. So if there is no questions, then we can close the session. Before closing, I have one question that you shown that the map, historical map of Indian Sundarban from 1776 or something 18. So these are the toposit, the how you will get this historical map of the green coverage
No,
or the forest coverage of this.
it has been actually mapped by a study. I have cited the source. I can share the paper with you also.
Yeah.
They have actually taken into consideration a map prepared by Mr. Rennell or something, who used to be the cartographer of the British rule before Dampier and Hodges actually demarcated
Line.
the line. So from that map, that has been digitized by someone. It is not that I have done that. I have actually cited the paper, and with the best possible efforts of digitization, they have tried to show that mangroves were actually up to the periphery of Kolkata. So, for example, many of the people
Yeah.
in the
Yes.
attendance, they don't know, because where Dr. Datta used to stay in India, where I am right now giving this lecture, everything was dense mangrove forest in 1776. But now the mangrove forest is almost 50-60 kilometers away from the periphery of Kolkata. So that is the extent over, means in the last 2 centuries, what we have done to the mangroves.
Okay, so and one last questions from my side that yes, blue carbon you are considered that mangrove, seagrass or the kelp forest or the yeah. So what
Sorry.
about the salt marshes? So what about the phytoplankton?
Phytoplankton is also, actually, there are many schools of thoughts who wishes that phytoplankton, not only phytoplankton, they are actually willing to include fish. Okay, because they are also sequestering carbon in their body. They are
Yes,
also dying. If you do not eat it, they will die and they will fall in that floor. They will decay
exactly.
and the carbon from them will get inside.
Definitely. Yes.
I guess my best guess is that including phytoplankton into the blue carbon ecosystem can become a reality. I am not the authority of blue carbon who decides that what will be a part of blue carbon or not. But the practical problem is that to actually estimate and understand how much carbon the phytoplanktons are having, because phytoplanktons are always in a part of an ecological food chain. What is phytoplankton today is food for zooplankton tomorrow. What is zooplankton today is food for a small fish. So are we actually in a place to actually take into account all the marine ecological food chain and imbibe the same into the blue carbon arena? And actually, can I tell that how much amount of carbon will remain in that sediment, which is simply a product of the entire marine ecological food chain? I think science is trying to, make some breach in this particular dimension, but the estimation part is still very challenging. Unless you can properly estimate how much carbon is going to remain, if you cannot answer this question, it is very difficult to include newer dimensions into the blue carbon ecosystem.
Exactly. Exactly. Yes. So, any more questions? If not that, then we'll close the session. So, as I already told to you that it's a kind of series we are conducting the related issues on marine science and fisheries, a series of webinar. So next webinar will be make somewhere sometimes, and also will be in any topic related to the marine science and oceans. Okay, so if not no more questions or discussion, so then we will close the
Sorry,
session. Yes, yes,
sorry, Dr. Chanda.
yes.
First
Yes.
of all, it was nice and good presentation. Thank you so much for that.
Thank
I'm
you.
from Tanzania, Zanzibar, and I
Oh,
have very
great.
small one question. I would like to know which mangrove species is most effective in carbon sequestration.
Okay. No, this is a very good question. Actually, you know what happens. You are from Tanzania.
Yeah, sure.
I shall pass on my book. I tried to have some literature review when I was writing the blue carbon dynamics of the Indian ecosystem. I actually took into account all the peripheral African nations as well: Tanzania, Madagascar, Kenya, Nairobi, Somalia, and everything. The blue carbon aspect that you are talking about. When I tried to look at the western part of the Indian Ocean, I
Yeah.
found some stark difference that I observe in my study area and you shall observe in your study area. Say, for example, in Indian Sundarban, there are 35 true mangrove species. But if I am not wrong, I cannot exactly remember. In Tanzania, in Zanzibar, if the species diversity is concerned, I think it is around 17 to 18 species, somewhat like that. So
Okay.
now mangroves will not act species wise in throughout the world. That is the fundamental idea that I'm trying to share with you. Because if I measure a particular carbon content of a particular species in Indian Sundarban, and if I measure the carbon content of that particular species just 100 kilometer downstream in India, the same species will show me that it is behaving as a much higher carbon stock in some other region and very poor carbon stock in my region. The same species. So
Okay.
it is not the species that regulates the carbon sequestration potential. It is the abiotic factors that are governing the species to grow at its healthiest best. Okay. So
Yeah,
like
sure.
Sundarban. Do you know? Let me tell you a funny story. The word Sundar in the colloquial language of Bengali, it means beautiful. Okay, it means beautiful. Sundar. So Sundarban means beautiful forest in Bengali. Okay. Why it is called a beautiful forest? It is called a beautiful forest because of a tree. Okay, because of a tree which we Bengali people in India, we call that tree Sundari. What is Sundari? Sundari is Heriteria fomes. Are you aware of this tree?
Yeah, sure.
Sure. Heriteria has two subclasses: Heritiera fomes and Heritiera littoralis. Okay.
Okay.
So Heritiera fomes at some point in time in Indian Sundarban, it was dominated by Heritiera fomes.
Okay.
And I have found out that Heritiera fomes in Sundarban, that Heritiera fomes has the highest carbon sequestration potential. But
Oh,
today there is no Heritiera fomes, almost no Heritiera fomes in the
Very well.
natural Sundarban. Yeah. So now if you ask that what is that, why did it happen?
Pieces.
I have already explained why did it happen. But even if I plant a Heritiera fomes today, Heritiera fomes will not be able to sequester carbon at all. But if I just go 100 kilometer down in another state named Orissa, there is a forest also. There is a very good mangrove forest, Bhitarkanika, in India. I'm talking in India.
yes.
There we have 5-story building like Heritiera fomes. You cannot actually embrace that stem. It is so huge. But
Yeah.
that same Heritiera fomes is not functioning in my Indian Sundarban because I have changed the abiotic attributes of Indian Sundarban. So yes, it is true. Species-wise carbon stock varies. True. But you have to first look that is your species healthy? Is your species able to grow in a healthy condition? Then only you will be able to understand the potential of that species. Okay.
Yeah. Okay. Yeah. Okay. Okay,
Thank
doctor. Thank you so much. Thank you so much. It was
you.
clear.
Most
Very
welcome.
clear.
Yeah.
Okay, okay. So if not, then yeah. Anyone want to ask any more questions? No. Okay, then thank you, Dr. Chandra, for
Most welcome.
wonderful lectures, and we hope later on we will also again, and we also hope to make some collaboration, also to do some blue carbon dynamics in Oman coast also. Uh,
Sure.
yes, yes. Okay, okay. Thank you all
Okay.
for
Thank you.
participating, and who have participated, they will receive the certificate over email. Okay.